because we know that's part of the story. Steady state is part of the story, and the story also means obeying those Bewegungsgesetze. So those of you who don't know how to speak German, you just learned a good word today. So welcome to the sixth lecture. We're going to talk about the Ramsey Model for the second and last time. But Ramsey will come back to haunt us. The ghost of Ramsey will come back in many, many instances in the rest of the course because we've learned a technique which can be used in other circumstances. I guess some of you may have been paying attention when you saw that Paul Romer won the Nobel Prize this year. He's sharing it with William Nordhaus. Those two areas of research are very related. One is the environment and the other is economic growth. And Paul Romer has written several papers on growth theory. That's his thing. And one of the things that you do in that model is to look at how people's activities in research and development affect total factor productivity. Okay? And the key word there is externalities. So if I do research and I produce a great idea, then the whole world gets to use it, basically. Even if you pay me lots of money for the Nobel Prize, it ain't enough to compensate for all the good I've done for the world. And similarly, if I dump a bunch of chemicals in the ocean, I hurt a lot of people and I don't pay for it. So these are called externalities, and that's what growth is about to some extent, when growth occurs because of external effects. And one of the ways you can figure this out is to ask what the planner would have done. Okay, so using the tools that you're learning now and last week help us think about the planner's optimum. If the planner could actually control the amount of research and development an economy does, then would it make a difference? Could we be better off than if we just let the market go on its own? So that's the methodology that's also used in environmental economics, except it goes in the opposite direction. If you produce a lot of stuff and you dump a lot of chemicals, treating the world like your backyard and not paying for it, then that's a negative externality. And that also has an effect on the environment and on possibly also on growth. So those two guys won the prize for that, and you should keep that in mind. It's kind of an interesting way of linking up to what we're doing here, because one of the things that Romer did in his papers that got him the Nobel Prize was apply this method, okay? The planner's problem compared to the market, and see if there's a difference. As we've done, we'll do that again today for the last time in this very simple example. Okay, so we'll review last time. We'll introduce a tool that will help us think about this issue, and it's a two-dimensional graph. So you can't always use graphs in complicated instances and circumstances, and later in macro you'll have to use the computer, but at least this will get your mind around some of the ideas that we're going to discuss for the next few weeks. And this is called the phase diagram. So it's taken from physics. It's basically a way of thinking about how an economy not just moves from one steady state to the next, like in the Solo diagram. It's actually going to ask how we get there in more detail than you had in the Solo diagram. Okay, so that's just a little preview for you. We'll finish that. We'll talk about normative versus positive economics. The first part of this lecture will be on the normative question, the Ramsey question. What should an economy do? What should a social planner do? A benevolent dictator that wants to help people be as happy as possible given their budgetary and resource constraints. And then we'll contrast that with the positive economic question, which is how do economies actually behave under certain idealized assumptions. Okay, so we'll talk about the decentralized economy. We'll perform a decentralization of the planner's problem and ask whether the planner's problem's optimum can be attained by a decentralized market. Usually the answer is no. If we're really honest economists, right? We're not just ideologues. It's very hard to achieve the first best. Okay, but we should be aware that it's possible, and we should be very clear about the mistakes that we make if we assume that everything works in a market, because sometimes it doesn't. There are all sorts of reasons, and you should be able to rattle them off. One of the things I did when I was in graduate school was have to state all the reasons why the decentralized market solution fails to achieve the social optimum. Okay, so it's kind of It's a good way to counter arguments on both sides. Just be able to understand why markets don't always work. We do think they work a lot because they decentralize a lot of activity, and they actually bring people to the point where they implement decisions that reflect their private interests, which often lead the market to do the right thing in the aggregate. That's kind of the hope and the belief that we have that goes back to Adam Smith. Okay. I'm going to give you some policy implications of the Ramsey model. One of them, of course, is Romer, his work on innovation and endogenous growth. We won't do that in this course, but if you take Florentina Schwartz's course on growth theory, you'll be able to see that in all gory detail. And the methods we do today will help us understand that. And we'll also discuss some modern interesting conundra like real interest rates. Why are real interest rates so low? Well, the Ramsey model can help us understand that. There are some good reasons. It's not monetary policy. Later we'll talk about monetary policy models that could also explain why nominal interest rates are low, but the observation remains that real interest rates are low. It's not just nominal interest rates, it's real interest rates, and they've been really low for a really long time. Okay? So if you think that money is neutral in the long run, maybe there's something real going on that we should understand. And the Ramsey model can help us understand that, at least at a first approximation. Good morning, everybody in the back. Good to see you. Good morning. Okay, so last time, you missed my motivating speech. We're going to motivate Ramsey's idea again. We're going to talk about the Ramsey problem because it's important. The technique last time we're going to do again, the maximum principle. It's like cookbook Lagrange multiplier approach for the static problem, now applied to a whole intertemporal problem with continuous time. So it's a really fancy problem, fancy answer. And I'm not asking you to prove any of this stuff, but if you're interested, I can give you some great references. If you're like Michael Intrigligator's textbook on mathematical methods, it's great, but it's really, you just want to, as a master's, you really only need to know this, but you need to know it well, because it's very likely you'll see it on the final exam. Okay, we talked about the necessary conditions for an optimal path. Remember, the social planner, Ramsey, is choosing the optimal path of consumption from t equals 0 to t equals infinity. He's choosing a function. He's not choosing a single value of consumption. If any of you guys make that mistake in the final, I will really be disappointed. I would be hurt, okay? Because I've said it 3 or 4 times already. It's a function, choosing a consumption function of time. So you're characterizing an optimal policy, and when you choose a path of consumption, you're simultaneously choosing, given the capital stock initially, a path of investment and future capital stocks. You can't choose the capital stock in any instant of time. You have to work at it. So we've already isolated the idea of a state variable versus a co-state variable or control variable. The state variable is the variable you cannot change at period t. You can only change it in t plus epsilon or a little bit more than epsilon by doing something between now and then. Okay, so that's a very important idea in continuous time. So already we see that consumption is a control variable. Ramsey's choosing your consumption from now into eternity. He's going to try to make you as happy as possible by maximizing an integral of this u function, which is your utility at every point in time over your consumption. And you have increasing consumption in a level and a decreasing marginal utility. That's basic neoclassical economics, goes way back in time. And we've got a capital stock, which is our state variable, which basically governs the productive activities that we can undertake right now. Given that capital stock, we can produce output, and output we can allocate to our own consumption or to investment in the future capital stock. Okay, so this is like the Solar model, except it's controlled. It's not an assumption of savings rates. It's basically you're choosing the savings rate. The rest is obvious. Okay, so all these things we used to write down this problem, which looks nasty, but now you know how to solve it. You're choosing this function to maximize this integral, which is a number, and this is certainty. We haven't gotten any uncertainty yet in this problem, but you're choosing basically this evaluation of a stream of consumption that is feasible, that meets the second line of this slide, which is the feasibility of my being able to sustain that consumption by saving today and accumulating capital over the next instance in time, looking forward. So the succession of those equal signs is just a reduction of that intertemporal resource constraint, which is not a single equation. It's an equation that's valid for all points in time. It's not valid for a single point in time. So, it's just like in the discrete time analog we did before. This is basically the rules of your game. But it's not just true in t equals 0, it's true in t equals any t from t to 0 to infinity. So that's a hard problem to solve unless you know how to do the calculus of variations, unless you know how to do the maximum principle. And you're further restricted by getting the initial capital stock at the beginning of time, right? So you have this K0 to deal with as well. So if you're in Senegal or you're in Angola, you have a different initial condition than if you were in Norway, okay? And that changes the game. You cannot wish for extra capital. You have to basically make it. Okay, these are common. So the principles for optimality, if you can write down that objective, you can write down a Hamilton function, the Hamiltonian as we called it. I won't write it down again, it's already been done, and Andreas did it in the section, and we'll do it this week actually. You set up the Hamiltonian, and then you just take these rules and you play with the Hamiltonian. You write down first order conditions, necessary conditions for optimality, which involve the control variable, that's number one. Number two, the state variable. Okay, that's number two. And in our particular problem, control variable is CT, so at every point in time from 0 to infinity. And the state variable is little k, capital per capita. And these derivatives have an important interpretation, as I said before. Think of the Hamiltonian as like a mountain, and you're trying to climb this mountain. So the first thing you want to do is set the control variables to have gradients, okay? And these gradients have to be, when you're at the top of the hill, basically at every point in time, you want that Hamiltonian not to be increasable. So the partial derivative of this Hamiltonian with respect to CT is equal to 0. You've reached the top of the hill. At the same time, you've got to obey your sort of side constraint at every point in time, because your capital stock is moving, because when you consume, you're not investing. And if you're not investing, your capital stock will be doing something that you have to pay attention to. So that's why the second set of derivatives, in the second derivatives from t equals 0 to infinity, say that the state variable, okay, has to change in a certain way such that the effect has to equal the effect on the co-state variable. And the co-state variable is the Lagrange multiplier in this case, okay? So that's this mu. We'll see the exact implementation in the next slide. It's a really good idea to download the slides and look at them. You already have the ones from last week. This is a repeat, okay? Okay, so first off, you have to identify what is the co-state, what is the state variable, and then you impose this final thing, was just to make sure that you don't make a really big mistake, you don't accumulate too much capital for the rest of eternity, and you say, gee, I could be eating some of this capital every period, and I would actually be better off, because the first two sets of first order conditions are just necessary and not sufficient conditions. The last one is called the cake eating condition, right? If you have some cake and you put it in the refrigerator, you love that cake, oh, I love it, I'll just leave it in the refrigerator. Next day you keep, and this cake is really durable, so it's got all sorts of antibacterial stuff in there, and you realize after several hundred years you've still got the cake in there, and you keep putting more cake, but you never eat it. So you want to eat it. In present value terms, you want to be able to, otherwise you wouldn't be optimizing. Just kind of common sense. This is a very common sense approach to this. We could do it in a more mathematical way. It's bad enough if you look at these equations, right? This is the implementation of those equations in this very simple model. One state variable, that's the capital stock, and one co-state variable, okay, which is, it's the Lagrange multiplier in present value terms. It's also going to be a transform, a monotone transform of the control variable, which is the consumption at every point in time. Okay, so I'll just repeat this. The first equation has this wonderful interpretation of the marginal utility at any point in time of a little bit more consumption has to be equal to the opportunity cost in utility terms of consuming, and which is basically its value in the resource constraint. So if I don't consume today, I'm like dropping a little bit of consumption into the bucket of capital accumulation. So I'm getting a bit more capital. What's that worth it to me? That's worth lambda. Lambda is the shadow value of capital at every point in time. It is also a function of t. Okay, so this lambda, it's something that helps us understand the problem. Because if we're doing everything right, lambda has to behave in a certain way. Okay. Now, the second condition involves the Hamiltonian differentiator with respect to the state variable, and you set that equal to the negative of the co-state variable, which was mu, present value of the resource constraint in each period. I'll make the substitution in a second that'll help you understand that, because the trick we're looking at is relabeling the primitive present value multiplier, which is mu in the Hamiltonian, as the current value discounted to period t equals 0. Okay, so in other words, we do this substitution. We're going to substitute for this should be a row, by the way. It's going to be a row later. Sorry, mu. No, this is perfectly fine. I'm just a little bit off today. So the substitution is for mu t, and we're substituting lambda t discounted using e to the minus theta t. Theta is the discount rate. Okay, so the social planner and the individual have the same discount factor in the Ramsey problem, and then we just have to go back and forth and basically calculate this object. Okay, so that object turns out to be this thing using the rules of differentiation, having substituted for mu using this formula. Okay, and I've even put this on a slide for you just to remind you what happens if you differentiate Euler's constant raised to some number, some function of t, okay? So this last object is what we're going to substitute, and the reason we do this is because we can eliminate e to the minus theta t. And if you do that, you get this much more interesting looking object for the second first order condition, which says that the social planner has to choose his path of consumption or her path of consumption to make the marginal product of capital in each period equal to what's on the right-hand side of that equation. So you've got the growth rate of the population, you've got the impatience of the central planner, you've got the depreciation rate, and you've got the rate of change in this multiplier. So as long as we're moving to a new steady state, the capital stock has to obey this condition that the valuation, the marginal valuation of capital at each point in time has to be changing in a certain way that fulfills that last equation. Think of that as the capital gain. The social planner has a valuation of capital which is equal to lambda. So as we move through time, the social planner is like playing an arbitrage game. When capital has a very low marginal product, in some sense, it's because the marginal utility of consumption is changing over time to fulfill this equation. So it would mean basically the marginal utility of consumption is rising over time, meaning, it's falling over time because this would be negative, and negative is positive. Okay? So these are the three conditions applied to a very specific problem. The three cookbook rules, three first order conditions. This one's easy to understand. At every point in time, the marginal utility of consumption to this planner is equal to the opportunity costs of having it in the capital meat grinder, accumulating capital over time. The second one says that the path of capital has to be such that if it's rising, the marginal utility of consumption must be falling. Okay, so you make people really desperate. At first, you're going to make people save. Of course, you have to make them save to accumulate more capital. And over time, as you approach the new steady state, this term in the end goes to 0. And then we reach the steady state. Okay, so what I'm going to do now, I'm going to take those two equations, and I'm going to put them in a diagrammatic form to help us understand them. Okay, so here they are. This is the next page is basically eliminating lambda. I told you lambda is like a crutch to help us solve this problem. Okay, we're not going to ever observe lambda in real life. We can try to estimate it, but we can observe consumption, and we can observe the capital stock. We can observe population growth. Okay? So I can basically differentiate this equation with respect to t, and I can obtain, if you like, all sorts of terms that would contain ct, c dot, okay, dc dt, and I can eliminate lambda from the rest of the system. And I can get these two equations that are in a box for you. I have two equations, two differential equations in two unknowns, c and k. And those are things I can observe. I can actually measure them. Okay? Now, the first equation says that c changes, c dot is a shorthand for dc dt. So it's the change in consumption per capita per unit time. And I'm relating that to something that looks familiar to you probably. It looks like our Solo model. It's kind of the difference between the marginal product of capital and kind of this, if you like, the warranted or deep capital deepening line condition that we had from the Solo model. Okay? So we learned that consumption per capita will stop moving when those two are equal. And this thing, okay, I'm going to manipulate that. I'm going to massage that in a little second. I just want you to understand, we're making a statement about how consumption changes as a function of the level of consumption and the level of capital. So it's what we call a system of two differential equations in two unknowns, c and k. Now, I'm not going to ask you to solve that. Those of you who take in math, solving differential equations is, is one of these things that you can do it. Sometimes you can't explicitly. You can always do it numerically. All I want to do is do it visually for you, because we know that growth is about moving things, and we also know it's about moving things at certain speeds. The second equation is easy for us. That's just the capital accumulation equation that Ramsey has to obey from the get-go. He has to obey that. Right? The absolute change in capital per unit time is a race between what Ramsey is able to produce with his current capital minus that which he gives to his minions or her minions. Okay, Ramsey could also be a girl, right? Minus the warranted amount of change, because if the economy's got capital, it's going to depreciate, it's got to replace that. And if people are growing in their numbers, they're also going to be taking per capita more of the capital away. Okay, so it's a race. But we already understand this equation. We've had this one since the beginning of the semester. Okay, so we have two equations. Now note that k dot also depends on the level of k and the level of c. So we have two differential equations in two unknowns. Like I said, if you're a mathematician, that turns you on, but you don't even have to be a mathematician to be turned on. This is economics, right? We can see how the economy has to be moving to get to where it's got to go. And we haven't done that yet. Because remember, in the Solo model, Solo just wrote down little s. Germany saved 25% of its GDP, period. The United States saves 15% of its GDP, period, or 20%. China saves 40%. And then we get this answer. It's kind of it's not satisfactory. So we're trying to do better. Ramsey's idea, was to do a little bit better. Now I'm gonna massage that. Look, I go from here. First off, I erase the stuff at the top so you don't need it anymore. Then I divide left and right on the first equation by CT. So what is the left-hand side? It is the rate of growth of consumption. It's the change in consumption per unit time divided by the level of consumption is the rate of growth. So it's like the gradient. It doesn't have any units. Okay, so you can actually calculate that for any old country. And then on the right-hand side, you've got the same old wedge between marginal product of capital I got right now and what I need to keep it kind of stable. And then I've got this guy. What is this thing? This is a very special object. This is kind of if you think about utility theory, this is the readiness of trading consumption today for consumption tomorrow or in the next instant of time. It is the elasticity of intertemporal substitution. Okay, it's the readiness, and it's an elasticity, so it doesn't have any units, and it's also bounded by 0 and infinity. If it's 0, that means I'm not ready to trade off consumption. I like consuming CT constant every period, or I'm really, I'm going to really move my consumption to the period where the rate of return is the best. Okay, so If this thing is infinite, I would really push my consumption into the future if there's a slightly higher rate of return in the taking me into the future, or vice versa. Okay, so those are very extreme values. What reality is somewhere in between. So usually we think of the log utility function. That object, which I'm going to call sigma, is the elasticity substitution. In the log case, because you can take any old u that has the properties I wrote down, and you can calculate this thing. It doesn't even have to be a constant. It can be changing, right? If you take the log of c, the log of c has a constant intertemporal substitution elasticity of 1. Special case. That's why Andreas likes it so much. Andreas didn't come today, right? Is he out there? No. Okay, so Andreas, he likes the log function because it has a really nice property. It's easy for you to play with on a problem set. Okay, so that's sigma equals 1. Everything else in life is kind of more complicated. It may even depend on consumption. So the level might actually affect the elasticity. That's life. Okay, but there's a class of functions called the isoelastic functions. Okay, power functions with a certain restriction on the power will give you a sigma that's constant but not equal to 1. So we've already given you some little technical stuff there, right? So I call this Ramsey's system of two equations in two variables, consumption and capital per capita. Okay, so just to review, I'm trying to go slow for you because I'm going to take these, I'm going to put them on a picture, and we're going to have this wonderful picture which is going to help us understand this. Okay, and the second equation looks like the Solow model. It's no different. So there's a bit of robustness in what we're doing, looking backward into time. Ramsey was pre-Solow and anticipated it, okay? Just shows you there's some universal things in economics. And the first equation is basically this readiness for the central planner to move consumption forward and backward, or from the present to the future, by investing more or less. So you can see, obviously, this is always positive. So if F prime, the marginal product of capital, there are no interest rates in this situation, right? And Ramsey's just controlling stuff. The central planner is allmächtig, right? This woman is just running everything, okay? So when this thing is high relative to these constants, that means that consumption must be growing per capita. She's making her people save today to get more tomorrow. Okay? It kind of sounds like China, you know? China is saving a lot right now, so maybe China's run by a central planner, and that's what they're trying to do, you know? It's called the gradient, the consumption gradient. Okay, it's the rate of change of consumption. And indeed, if you look at the data, China does have a pretty high consumption gradient right now. Germany, not so gradient. Okay? It's more like 0, maybe a little bit positive. Okay? There was a time when it was 0, and now it's kind of picking up a bit. So this model actually has an interesting content. It's not a joke. Okay? It's a serious model. We call this the Keynes-Ramsey rule, named after Keynes and Ramsey. Okay? And Keynes actually gave Ramsey the interpretation. So Keynes was teaching Ramsey, said, look, hey, Frank, why don't you put this spin on it? You got this math here. Why don't you think about it like this? And then he's saying, well, consumption is growing. It's actually growing at the rate that the central planner is incentivized to make it grow. So if capital is not very productive relative to population growth, impatience, and depreciation, then consumption ain't going to grow much. Why should you save? It's not very productive. Just eat it. Okay? Right? So that's a characterization of doing the best you can. Okay, so the Keynes-Ramsey rule, consumption increases per capita or remains constant or falls depending on whether the marginal product of capital relative to population growth and depreciation is greater or less than the rate of time preference. So if Keynes's central planner or Ramsey's central planner is very impatient, then theta is high. Okay, so you're more likely to have flat consumption. But if you're very patient, then you're going to have a high gradient. Okay, so again, this is kind of, and I'll come back to this when we talk about Draghi. A lot of people blame Draghi for low interest rates, but interest rates were low before Draghi. Okay, they've been low for a while. So we need to think harder about the real economic determinants of interest rates. It's not just monetary policy. This is the real economy. There's no money in this economy. Okay? And we're talking about trends over 20 or 30 years of experience. And I grew up in a period when real interest rates were very high. I grew up in the 1970s and 80s, 70s. And the 80s, they were high too, right? So you might say, well, why were they high back then and not so high now? So it's not just monetary policy. Now, there are people who disagree with me on this, but most people agree with me. Okay, so there's the, I just restated the Keynes-Ramsey rule. The rate of growth of consumption related to the marginal product of capital versus the warranted or capital deepening condition that we have from Solow. And of course, this readiness to trade off depends on your elasticity of substitution. Okay, it's not dependent on impatience. It's just how much curvature your U function has. If your U function is really cool, then you actually don't like to trade off much. Okay, you're going to try to focus or keep your consumption relatively stable. But if you have a flat U function, then you're going to be really kind of, bang, bang, move the consumption in a very costless way to where it's most valuable to you personally. Okay, so now we've got this differential equation system. Now we're going to ask the obvious question. When you see that equation system, is you ask, what is the steady state? Right? This is like Solow. First you say, what happens when everything's calm and peaceful? So C dot equals 0 and K dot equals 0. Now, some of you are looking out the window right now. I think that's a mistake because I'm about to show you something really important. So pay attention, right? Keep your eye on this ball. When C dot equals 0, we're at the Solow steady state. So it shouldn't surprise you because the model is kind of based on Solow. Okay? Except now we got a little twist, which is Ramsey. Ramsey's impatience is in there. Okay? So we've kind of shoved a little bit of extra stuff in there. It's almost like what we had in the Solow model, except now we get a bit more tilt coming from impatience. And Ramsey said you shouldn't be too impatient. You should care equally about future generations and people. So he would set that equal to 0. Then we're back in Solow's world, maximizing per capita consumption. Okay, but indeed, that ain't the case if you have impatience. Okay? We call this the modified golden rule. We talked about that already. And it's a familiar condition from all the other stuff you've been doing. So there's a lot of unity in what we're doing today with the past. Okay? So take that condition and think about it for a second. That has implications for what C dot is doing at any point in a plot, a diagram of C versus K. That is the phase diagram, which you're about to see. Now, notice all of you are not looking out the window now, which is great, because here it is. That is the phase diagram showing the law of motion for consumption at any point in that diagram. For any pair of consumption and K, C and K, I can tell you what the arrow is doing. Is it going up or is it going down? If it's going up, it's rising. If it's going down, consumption's falling. And if it's 0, we must be on the condition. So that line must be the C dot equals 0 line. This is all about logic. It gets even better. Okay? So everything to the left of the C dot equals 0 line, you have rising consumption according to the law of motion for consumption. And everything to the right means that consumption is falling. So anytime the model obeys the social planner, it has to be obeying those laws of motion. That's the first one. That's going to help us understand how we get from one place to the next. The law of motion for the Solow resource constraint, K dot equals F of K minus C minus N plus delta times K, looks like this. The Solow condition of steady state capital stability is K dot equals 0. It doesn't look like a monotone function anymore. It looks like a hill. Okay? And everything that's under the hill, capital is rising. And everything that's above the hill, capital is falling. That's just the way it is. That's the math. Above the hill, capital is falling. Below the hill, capital is rising. Why am I going horizontal? Because it's about K, and K is on the horizontal axis. Sorry to be so pedantic, but this is important, okay? So look, down here, K is growing. Here, K, it's kind of weird, isn't it? But those are the laws of motion. You can't break the laws of motion. Gesetze, Bewegungsgesetze. Actually, Karl Marx used that word in Das Kapital. Bewegungsgesetze. Okay? So these arrows have to be valid at the same time. So any point in that diagram has to obey those arrows, and those arrows add up. So if I have an arrow that's going up like this, and I have an arrow that's like this, the net of those two arrows is that one. It's not vector calculus. It's just adding two arrows. Okay? Okay, so if I put the arrows together, I can see if I take an arbitrary point on this diagram where the economy has to go in the next few instants. And if I know that, then I know where it goes in the next few instants after that. So you can see some of these paths look pretty weird. Some of these paths are not going to be feasible. And the central planner is trying to maximize your utility. So he ain't going to just choose any old path. He's going to choose the right path that gets you to that little green dot. Because we know that's part of the story. Steady state is part of the story. And the story also means obeying those Bewegungsgesetze. So those of you who don't know how to speak German, you just learned a good word today. Bewegungsgesetze. German words are so big, Mark Twain said that German words are so big, they have perspective. Anyway, so the point is we're going to use these arrows, and we're going to use the sum of the arrows to find out how do we get home? You're lost. How do I get home? We got to get to that green dot. Okay? And we know that it's not so easy. I'll just tell you something. If you just pick a point over here, if I just pick that point, where do the arrows point? We ain't going home. So what does that mean? That means that consumption's rising and capital's falling. And it's not going to stop. Okay, so if you're there, you aren't coming home ever. You're going to go here, and you're going to go to there, and then you're going to go to there, and you're going to get to a point it's implausible. You're going to have negative capital, no go. You can't do that. You're going to run out of capital, and you're probably going to starve. Okay, so that's bad. So being in this whole orthant is off limits. Okay, and similar, you could pick a similar orthant down here. Okay, to the right of the c dot equals 0 and below the k dot equals 0 line. You ain't coming home from there either. Okay, so we can rule out those two orthants. Any dynamic path that obeys Ramsey's optimality cannot be in those orthants. Okay? So what does that leave us? That leaves us this bit here and this bit here. And it turns out if you look carefully at that, it's not clear that every path that I just choose arbitrarily in those two orthants will get us home. Okay, so this is a really interesting fact. It's a fun fact. This model has one co-state variable and one state variable. The state variable I can't change. Remember, that's the rule. I can't change the capital stock right now. I can change it in a few periods if I work at it. Okay? So that means that I've got to choose my consumption in such a way that I get home. There's exactly one path that will take me home, and that is called the stable manifold. And if you want, the mathematics is quite interesting. It involves the eigenvalues of the dynamical system. Okay, they have to have a certain sign, etc. I don't want you to learn that stuff. I just want you to understand the geometry of it. See, if I start here, then there's a chance I might get home, but it depends on this one. So I'm going to probably try to choose a path that will pull me right into the garage with a path of growing consumption per capita and growing capital per capita. Everything else will lead to catastrophe. Okay, so this is called a stable saddle path or a stable manifold. Okay, and it's an implication of this theory. So remember, Ramsey can do whatever he wants because he's in control. And the social planner will do this if she's doing the right thing. If she's not doing the right thing. Okay, so the cool thing about this is we don't care about the free markets, right? We just care about this problem, and then we're going to compare the free market to this. So it is kind of exciting, isn't it? Okay, and the same thing is true from up here. If I choose the right combination of consumption given my capital stock, and that's all I can choose as the planner. I can't choose K. I can choose K in the future if I do the right stuff today, but the only control variable is consumption. So consumption will be chosen such that if I'm up here, I'm going to be shrinking my consumption and capital per capita to the point where I eventually come to the steady state where things aren't changing anymore. Okay, and that will satisfy all three sets of first-order conditions or necessary conditions for optimality. This is a very powerful method. Okay, you can do a lot with this. We can do what's called comparative statics. We can change parameters and see what happens. And it gets fairly interesting. So we can ask what would happen if we had a civil war, for example, that destroyed half of our capital stock. It'd be a terrible event. What would that mean? That would mean suddenly we're in a different place in this diagram. How do we get to the new point, we get to our new steady state? Okay? So if you have a civil war, that would imply something like, well, people's behavior hasn't changed fundamentally, but they've lost half of their capital stock. So how are they going to get back? That's one example of a question. But we could do other stuff. We can say, suppose my depreciation rate changed. Suppose we introduced a new type of capital that depreciates very quickly, has a very short half-life. What would that mean for my economy? That'd be like comparing the old and the new, and you could ask, how would we get to the new equilibrium? Again, it's challenging to think about this, not just because it's kind of hard, but also because philosophically, how could it be unexpected? This is a model of perfect foresight, so if I knew everything, then I would know that they were inventing this new type of capital, or that something like this would happen. So you have to twist your mind a little bit. Think of this as kind of, you're comparing two different parallel universes, and you're asking, okay, how would this one compare to this one? Okay, because it's still very, very interesting. It's intellectually challenging. It's also controversial, but we're going to do it. We're going to do it anyway. Okay, because that's what we do in economics. We do stuff that you can't do on real live economies. I would love to get Venezuela, under control and try to do some stuff with it. It'd be kind of neat to see what happens if we just stop printing money and, maybe freed up the markets a little bit, privatize the oil company, or maybe not. You can do all these things in your mind, but you can't do it in real life. That's what makes our life difficult. So we call this comparative statics. It's called comparative dynamics if we care about the path. If we just care about the point of intersection, it's easy. The cool thing about this phase diagram is it helps us look at the dynamics as well as the statics. Okay? So the static part is the steady state, and the change I'm going to talk about changes the steady state usually. If it's just a destruction of capital, it would just be moving away from the steady state and seeing how you get back. Okay, we could do that one as well. But right now I'm going to talk about changing some of these parameters. And if you do that, then you have a new set of intersections, and you have to ask, how do we get there? So this will involve using what I just said before, using the equations of motion for capital and consumption. Out of equilibrium, out of the steady state, out of the steady state. There's no equilibrium in this because this is a planner's solution. In a minute, we'll talk about equilibrium. Okay? So, which parameters could we vary? We could talk about the planner. Maybe she got really impatient. Or maybe she got real patient. Remember, patience in economics is one way of capturing impatience, time-consistent impatience, is the rate of time preference. Okay, so high theta means we're impatient. We discount the future very highly, and we want to do everything now. You could also think of getting patient means theta goes down. And the central planner is the same thing as the people she is organizing. We could also think about depreciation, which I already mentioned. We can think about population growth. As exogenous parameters, how would they change the situation? We can also I'll take this one into account as well. What would happen if suddenly, this could get much harder. I could do TFP, the rate of growth of TFP. I'll talk about that at the end, but I'm not going to do that. It's a little bit hard. What would happen if suddenly we became more productive one time? Just a one-off productivity increase. Okay? Because think about it. I mean, if we all became suddenly more productive, it might make sense to use some of that productivity to increase the capital stock so we can have more to eat tomorrow, not just eat it all today. Okay, so obviously this is a relevant question. Okay, so in the environmental case, what would happen if we had more resources? We'd want to dedicate some of that to our environmental improvement. Okay, if we have a windfall, what do we do with it? That sort of thing. But this is a production windfall. So let's talk about, let's go back to our funky diagram here and look at it again. What happens if the rate of time preference decreases from theta to theta prime? Okay, so if you don't like the philosophical problems with this, then you could say, well, we're just comparing two economies and seeing how they would adjust, or what would happen to their steady states and the dynamics as we move through time. So we're starting here, and the first thing to ask is, of course, which curves move? So you have to look at those two laws of motion and say, okay, which one involves theta? Which one involves time preference? Okay, so the good news is it's easy to see. It only involves one of the equations of motion. It only involves the c, right? C dot equals 0 implies the marginal product of capital equals n plus delta plus theta. Population growth plus depreciation plus time preference. So that baby moves to the right. It shifts to the right. Okay? Now, don't look at the purple stuff yet. Just bear with me. The first part of this is to identify the shift. The second part is to identify the new intersection point. And then you're going to have to ask in the third part, how do I get there? Remembering that capital is a state variable. I can't change the capital. I'm in this new situation, so I'm obviously not in the steady state. How do I get to the new steady state given all the horrible things that could happen if I'm on the wrong point and end off wandering off the edge of the universe? Right? I showed you already that a lot of the paths in this model are automatically unstable. If I'm in the northwest or the southeast quadrants, I'm in trouble. Okay? But all I can do as a planner is choose C. I can't choose K because K is given at every point in time. Okay? So started here. All of a sudden, I've got a new C dot equals 0 locus, as we call it in economics. How do I get to the new dot, the new green dot? Well, consumption has to fall immediately. And consumption can move as much as you want, as much as you, central planner, wants. Okay? So because of the decline in, what is a decline in theta, decrease in the rate of time preference, okay? This would mean basically I'm going to become more patient. I'm willing to put more aside for future consumption. Okay? I'm not more productive. The capital stock productivity has not changed. The capital stock is no more productive tomorrow than it is today. But if I have more of it, I can eat more, and I'm more patient, so I want to push it into the future. So you can see what happens. I go on a diet and start saving in terms of capital, moving along the steady manifold to the new point given by the green point above and to the right of the old one. Okay, so that traces out optimal policy for a planner. Suddenly has a lower rate of time preference, more patient. Okay, this is a great example. It's a good start. It's an easy one to start with. There are harder problems we can think about. We can think, what happens if we suddenly have a new technology, different problem now, which says suddenly the depreciation rate is higher. And I like this one because it has a lot to do with what we see today. We see a lot of technology that implies, even though we like it, it involves a much higher rate of depreciation of the capital stock that we have because the phones wear out, the computers wear out, the software is no good. It gets overtaken by other stuff, obsolete, becomes obsolete. So we can think of that as an increase of delta. So forget about theta. Now go back and we're going to reprogram your problem. We're going to think about delta going up. So this means different analysis. Which curves shift? If you stare at the two curves, you see now that both curves shift. Okay? Remember, C dot equals 0 implies that, and K dot equals 0 implies that. Okay, so you can basically trace through what happens. Both curves will shift. Okay, so we'll have a shift downward of the k dot equals 0 curve, and we'll have a shift to the left of the c dot equals 0 curve. But the logic of the saddle path and the convergent dynamics is the same. There will be exactly one stable manifold that will take me to the new green dot, the new intersection, the new steady state. Okay, so it's going to require a drop in consumption, and it's also going to involve a shrinking capital stock. Now, why is that? That's because at this new higher rate of depreciation, it don't make sense to save a lot anymore because capital is burning up. It's the rate of return on capital, effectively, the rate of return on savings, the return on capital net of depreciation has gone down. Okay, so people will, but people also feel poorer because in the long run, they will be poor. You cannot sustain a high level of economic activity if the capital stock is burning up like fire, okay? Because if you want to, you're gonna have to almost save everything just to keep GDP constant. Okay, so the point is, we'll have a one-off drop of consumption, then we'll have a new convergent dynamic with falling consumption and falling capital stock, which will cruise us right into this new steady state. So that's, to get that, you have to think real hard. You have to think about what's going on. And it's very interesting to think about our economy nowadays. We have exactly this going on. We have new technologies. We think it makes us happier. Maybe they do. Maybe consumption is not the only thing that makes us happy. Maybe we should put Facebook in the consumption function, the utility function, sorry. But if you know, abstracting from all that, if it's just about burning up more capital to keep everything, keep output the same, then basically we are poor, okay? I mean, again, if you don't get that, think about building a house. Build a house that lasts for 70 years in Germany. Maybe it lasts for, this house has been around for 100 years. Look at it, it's great, okay? It's not the same. So if you work hard and build something up, you're gonna have it for a long time. You're gonna be happy for a long time. If you buy one of these phones, I was happy when I got it, but it kind of goes away pretty quickly. All my Facebook friends are leaving me. Probably going to quit Facebook. Okay, so think about that. Old steady state, new steady state. How do I get there? One-off drop in consumption, capital can't change, and the new path is characterized by falling consumption and falling capital per capita. Okay, so that sounds kind of dismal, right? We are in the dismal science. This is economics. Okay, so these things can happen, okay? Other things can happen that make us happy, okay? So suppose now we have a new technical development which makes us more productive. Capital becomes more productive, so you are more productive, your children are more productive, and everyone can consume more at given capital stock. So how do we think about that one? Okay, so I'm gonna tell you the answer, but to do that, I've got to modify the production function just a little bit. I'm going to multiply it by A, which was equal to 1, so that's why you didn't see it. But now I'm going to let A be positive and greater than 1. Okay, so I've got A positive and greater than 1. It means suddenly I can actually produce more at any capital stock because I'm more productive. So this could be something like the invention of the internet, not software that burns up quickly, but rather just the fact that we can do more with our capital stock. That will make us all more productive. And it doesn't affect my C dot equals 0 curve, okay? Except for the fact that it affects the marginal product. But the marginal product, once I've reached the steady state, doesn't depend on C anymore, okay? So that the C dot equals 0 moves to the right, and the K dot equals 0 moves up. Okay, so here's what happens. To get to the new steady state, we've got to be in this orthant, and we can see that there's only one path that gets there, and I'm not asking you to find it, I'm just asking you to characterize it. Okay, so and that's what the math will do for you. It'll actually identify the stable manifold. It's a single path. It involves a one-off jump in consumption because we're all so happy. Hey, we're all so productive. We can consume more for the rest of eternity. Or our central planner says that. I'm vicariously celebrating his or her success. And I'm going to increase consumption one-off today, and along the new path, I'm going to be increasing consumption and capital at the same time per capita until I get to this new intersection, okay? So the impact effect is a positive effect. So this explains actually why this model predicts that new inventions that are understood by people lead to a one-off increase in consumption today, okay? Because I'm kind of saying that maybe the central planner and the decentralized market kind of move together, but the central planner would certainly be very happy. The marginal product of capital goes up and increases the tension between what I can get out of capital and what I need to stand still, and therefore I do more of it. So the whole logic is very, very clear, right? Okay, any questions about that? Yes?
We generally assume, or is it arbitrary, that line is to the left of the maximum force?
Which line?
Sorry, the vertical line.
The purple one? No, the purple.
The vertical consumption.
This one.
Yeah.
Well, it's in this particular case. Just look at it. Okay, and go back to your notes. Actually, I'll just show it to you again. This one. No. You have to go further back. Yeah. Okay. So you can see basically that what's key here is, when these things are equal, then no matter what consumption is, it's going to be independent of the level of consumption. So what matters is basically is this distance, which doesn't involve c. The rate at which you approach it does. Okay. So if you're very patient, you'll have a very steep approach, and otherwise you won't. But that's what makes it so easy to understand. That's why I put it in this course, because this line is vertical. Okay? So the right and the left are very easy to distinguish. Generally, that may not be the case. Okay, so more advanced models where you have, suppose you're talking about environmental protection, you have the shadow value of the environment, and you have the quality of the environment as a state variable, then you'd definitely have something like you have two curves that may have the same slope, actually. I have to check it. Okay.
And how would this change then? I'm just thinking, would it be different if the vertical line was on the right-hand side of the hump?
Yeah, great point. Okay, so he asked a great point. Now, Ramsey, or the woman who's doing this for him, are smart people, okay? They don't do stuff that's stupid. So if you're over here, you're probably inefficient, because we have this thing called dynamic inefficiency, okay? It could only involve a very negative value of theta. You're not going to have that. Theta is either positive or zero. Okay, so and remember, this is, if you think about it, this k dot equals 0 is actually something like consumption per capita. We want to make that thing as high as possible. So if anything, we're going to be on this side, but we'll never be on that right side. Okay, so now I'm going to take Ramsey, this brilliant UK economist who thought about the planner, and I'm going to say, maybe we can decentralize it. We're going to try, okay? And if you like this stuff, I can give you some great readings, but you don't have to do them. The Benassi book is good, and there's also this book by Blanchard and Fisher, okay? It's an old book, it's out of print, but it's very good. It's the same problem that we had before. Remember we had this OLG model that had people sort of being very selfish and thinking about only their own consumption when they're old, and then we gave them some offspring and that sort of thing. Well, now we're giving these people offspring to start with. We're thinking about a household that has an infinite horizon. So this is a dynasty. This is like a big family planning for the infinite future with some impatience. So it's a well-defined problem. Okay, and we're gonna. It's the same idea, except we've eliminated all the barriers to reaching the optimum, because people do think in the long run, and they think just like the planner. They have the same discount rate as the planner. Okay, the only difference would be, the only difference with the OLG model is that we don't have any disconnected people. So we don't have any migrants coming in. They don't have any, parents to think about them in this model, and they don't have a disconnect between their rate of discount and the rate of discount of the central planner, and they internalize completely the future. So they're not selfish or just a bit more selfish with respect to themselves. They really care about themselves and their children as if they were just complete, mirror images of themselves. Okay, so this is, if you like this, you can look at Benassi chapter 7. Okay, very similar. He uses a different notation. That's what kind of got me messed up this morning, earlier. But I stick to theta. Theta is trying to stick to the same notation. It turns out, and I'm going to take you through the argument, I'm not going to prove it, but under certain assumptions, the assumptions we have in this model, and when Benassi's rho is equal to my theta, okay, the social planner has the same discount rate as the representative family, the representative dynasty, then the social planner's outcome is actually replicated by the market equilibrium. So we're going to think about a market in which you don't know what the planner is, there is no planner, but you have a market for capital. You can buy it and sell it. You can accumulate it because everyone's the same. You only accumulate because you can rent it, okay, but everyone's the same, so the market price will basically reflect exactly the way you value it internally. I'll show that in a second. We need to add some notation because we didn't have any wages. The central planner doesn't have any wages. The central planner doesn't have any interest rate, but now we're going to put those in. Okay, so we'll see something that we can actually, open the newspaper and look for an interest rate. This is something we can actually find in the data. Okay, so the notation is almost exactly the same as the OLG model. So we've got consumption, output per capita, capital per capita, just like before, but now I've got a wage. The wage is the marginal product of labor in equilibrium, but not necessarily out of equilibrium. So we're going to the worker just knows that the worker, she goes to work and gets paid W, omega, each period. And the worker supplies labor inelastically, so the supply curve is vertical. Okay, so basically marginal product will be the outcome for this. Capital depreciates at the same rate, but workers, households save because they can rent their capital on the market and receive a gross return. Gross means per instant they get a user compensation. The user of the capital that they give the capital to gives them a payment of capital R. And R will include a compensation for depreciation. Okay, so obviously the capital depreciates. So in a sense, the payment to the owner of the capital will be big R minus delta in each period. So the real value of having a piece of capital in every instant is little r, and it looks like a real interest rate. It's like the real interest rate in each instant. Okay, so ultimately the owners of capital will be compensated for the depreciation, and in the long run they'll probably supply less of it if it's less profitable to do so. Okay, gives you another hint of where we're going. As I said, theta is the private and central planner's discount rate. The population is growing at rate n, and that's the growth rate of the family, okay, that the planner presides over. Now it's a family planner, it's not a central planner, it's the family, the household, that's doing the planning. And I'm just tossing in the rate of technical progress because we'll come back in a second, but I'll set it equal to 0 in this derivation. So now it looks a little bit like, but not identical to, the central planner's problem. The household's problem is now the household problem. It's the planning involves a budget constraint. It doesn't involve a resource constraint. It now involves a budget constraint. The numeraire is equal to the consumption good today. Okay, so the wage is paid in consumption units. So the household starts time in time equals 0 with little k 0. And remember, the household magnate, if you like, or the head of the household has a certain number of people in the household, and he has to divide this big capital stock by the number of people in the household. So that's why we still can work with little k. All right, so the household, I'm really sorry about that. The household is now in charge. Central planner is gone. The household faces wages and the rental rate of capital. These are prices that are set in decentralized markets, And everyone's the same, and there's common information, so the price that clears the market is the common one for everybody. So it's just a simple market. The wage is the same. So the planner of the household now, the household has a problem of choosing, given the path of wages that household knows to prevail over the future, and the path of rental rates of capital. The rental rate of capital is like the new incentive to save or not to save. Okay, before it was the marginal product of capital, but the marginal product of capital is being looked at by companies that are hiring the capital. Since the household only just looks at the price, and it turns out that's exactly okay. That's exactly what we want. And in equilibrium, that's exactly what the decentralized economy will give us. Okay, so pay close attention to that second line. That's the resource constraint of the household, which is like the budget constraint of the household. And because the unit of saving is the capital stock, there's no money in this economy yet. Okay, so the household basically carries capital forward to allow it to save in the future and produce in the future, but it does that by renting it out to firms that hire it, produce the output, and the household goes to work, owns the capital, and uses those proceeds to pay for it. So it's a completely closed system. All right, this is what, if you go on to take courses with my colleagues in macro, this is kind of like our bread and butter. Okay, so we have a decentralization of what the planner would have done. The assumption, of course, is that everyone's the same. It's what we call a representative agent model. Okay, so you're learning about the representative agent, and a lot of people criticize this. This model does not allow us to look at inequality. Okay, so we need to really tweak it to get a class of workers and a class of capitalists, maybe with some interchange. So it's we're still at the beginning of a very long voyage if you like this stuff. Okay, but it's a nice start. We need to get somewhere. We understand that people do face these incentives to save and to work. Okay? So given those conditions, you can set up the same Hamilton problem with different little bells and whistles. Now we have a wage. So the worker's labor input, which is exogenous, okay, will be compensated at the wage. So every capita in this household will get the wage omega in period T, and the household owns the capital, so the household gets compensated. And of course, when the Mercedes-Benz gets put in the garage, it will have depreciated, so you have to subtract off the delta K. Okay? I'm really asking you to stare at that differential equation. That is the budget constraint now of the household. It's not the planner's research, but it looks very similar, doesn't it? It looks very similar. Okay, so you can set up the same Hamilton problem, and Benassi does it in full glory, and Andreas will also do it in full glory. It's kind of like a replay, but with different players. It's not the central planner now. It's Big Daddy or Big Mama charging up the family's utility for the next 5,000 years, okay? In present value terms. So when you do that, you get a similar set of conditions for private optimality of the household. But they involve R and they involve W or omega, okay? Omega you can't even see because labor is inelastically supplied, so just kind of income. The household has to work in this model. More advanced models, the household can choose to work more or less. It's not a big deal. In fact, later on in this course, we'll do that. Okay, so you can see that I've reduced it to the same type of first order conditions. I've got this lambda, but this is now the lambda that belongs to the household. It's the household's valuation of capital at every instant of time from t equals 0 to infinity. This lambda has that interpretation of the shadow value in terms of utility of saving a little bit more. Remember, the numeraire in this game is consumption in period t, and that's the way we want to think about it. Okay, and the last period is, again, this is the private cake-eating condition. You're not going to be saving a lot and never actually use it in present value terms. Okay, so we can cook this thing down to the same pair of equations that we had before. The first one is the change in consumption with respect to time as a function of the tension now between my incentive to save, which is the gross rental rate of capital, minus some stuff which you could think of as the opportunity cost of accumulating capital as a private household. So like if you have a house in this model, you think about the house, that's your capital. So if you add on to your house, then you can effectively consume that later because you'll have more house in the future. But if the house is depreciating like really fast, like houses in the United States made out of wood and stuff, those would have a higher depreciation rate. You do less of it. Right? It's kind of stupid to do that. So, and if you have lots of people in your family that's growing like crazy, then you're going to have to really save a lot to keep them all in a house. So that's the way we want to think about this. So that tension is still important, and it's still important in the same way because we can transform to get a rate of growth of consumption on the left-hand side as the gradient of consumption, private consumption from the private household's perspective, as a function of the intertemporal rate of intertemporal elasticity of substitution times the incentivization to save, which is the race between the gross savings rate, the gross rental rate of capital minus the opportunity cost of holding it. And if you put the delta over next to the R, then you have something like a real interest rate. Cap R minus delta is the real interest rate. Okay, because if I have this house, I've accumulated more house, and then the house kind of evaporates, then it's not such a great return. The second one is my private household accumulation equation, which is kind of a race between my wages and my consumption, and basically what I get at the end of the day for my savings that I've accumulated, not for the savings that I accumulated in this instant, but what I've accumulated over the past since the beginning of time. That's little k. Okay, and of course it's going to be R minus delta, which is little r, and comparing that to N, which is the rate of growth of the people in my family, if you like. Okay, so we can redefine this model. It's this measure of curvature of the utility function, the felicity function, if you like. Call it sigma, just as before, except now it's not Ramsey's problem, it's your problem. It's your readiness to trade off. The firms are owned by the households, so the households internalize the budget in their budget constraint, the profits of the firm, and the firms in this equilibrium have no excess profits. The firms pay out to the wage, in terms of the wage, the marginal product of workers, and they pay out to the firms the marginal product of capital in production. So there's nothing left over. Therefore, there are no excess profits. Firms' payments to factors go back into the household's budget constraints. The whole household problem is internalized by the household. And that results from the linear homogeneity of the production function. So this is something we did at the very beginning of the semester. It's Euler's property of first order linear homogeneous production functions gives us that result as long as you have competitive markets. Okay, so you can see that the market equilibrium, where workers are paid their marginal product in terms of the wage, and the owners of capital get the marginal product of capital in terms of the rental rate of capital, means that product is exhausted, and the market equilibrium implies that the budget constraint of the household looks a lot like Ramsey's budget constraint. Okay? So that means you can see the analog between the market and the planner solution is pretty tight as long as certain conditions are met. Okay? So I'm going to finish by telling you why that's important. There are two economists who get a lot of credit even today, but they've got a lot more credit when they invented this. These are called the welfare theorems of economics. Under what conditions can a decentralized market reproduce the social optimum? This is not ideology of some political party. This is a mathematical economic result that you can actually prove. Okay? Ken Arrow, and I have his picture on the slide, and Gérard Debreu from France. They're both, Ken Arrow actually died last year. These are both very, very important economists and macroeconomists because they tell us exactly the conditions under which a decentralized market can come close to what Ramsey was promising us. Okay? And the answer is it's not always the case. So a good economist will be able to tell you when the welfare theorems of economics fail. Okay, so what's the first welfare theorem? Does anybody know? You must know this. You probably saw it in Micro. Georg Weizsäcker. Okay. Under certain conditions, planner's optimum can be replicated by a decentralized economy. Those conditions are like Adam Smith. Adam Smith wrote in the Wealth of Nations, the private actions of individuals can lead to an outcome that actually makes us better off, because we know that we get the meat on the table because the butcher wants to make money for him or herself. Okay, so the conditions under which that competitive behavior will actually yield the first best are pretty limited. So we already had constant returns to scale or less in production. So you can have decreasing returns, but you can't have increasing returns. So we say that, we call that convex production sets. That's the technical way of saying it. Non-increasing returns to scale. Secondly, no externalities. Externalities are impacts that we have on our neighbors that are not compensated through the market or charged through the market. Okay, so if I pollute the air, if I'm not paying the government for that, if no one's making me pay for it, I may be doing too much of it. Or if I'm innovating, maybe I'm not innovating enough, maybe people should pay me for it. So to get the first welfare theory to work, you need to rule out externalities. Externalities have to be internalized by the market. So if there is pollution, there is a way for you to make the polluter pay you for the costs that he's imposing on them. Okay? Third, full information. No dummies. Everyone has to understand what's going on. Okay? So these are pretty steep conditions. We also say you don't have to have no uncertainty. You can have, and that's what Aaron proved, you can actually have uncertainty. You just have to have complete markets. So that would be the fourth condition, complete markets. There are no missing markets, insurance markets, futures markets, conditions, contingent commodity markets. These conditions will give us the first welfare theorem. The second welfare theorem is the one that's even more interesting to macroeconomics. It says that if I have the planner's optimum, if I've identified the planner's optimum, I can support that by a vector of prices, okay, using trading, but I have to have the correct initial allocations of wealth to start with. Okay, so it's like, how can I reverse engineer Ramsey's optimum? That's called the second welfare theorem. Both of those you can actually look up. Arrow and DeBrew in the 1950s, 1953 or 1954, and you can look it up in the modern version, Mascalel. Okay, so that's if you really like microeconomics, that's the Bible of microeconomics. Mascalel proved this for continuous commodity spaces and uncertainty, all sorts of other crazy things. But these are really restrictive but interesting possibilities. So Ramsey is attainable under certain conditions. We should strive for it, but we should be very clear that in the presence of externalities, increasing returns to scale, incomplete information, closed markets, then this is not going to work. Okay, so that's the lesson I want to pass along to you. Take a look at the slides. Don't go preaching Adam Smith. Understand what Adam Smith himself said. He said that if you have monopolies, you have imperfect competition, these things can prevent us from achieving the social welfare optimum. Okay, sorry about the screw up with the machine. We'll get it fixed next time.